So let's talk about hydride reductions. If we look at a ketone and want to add sodium borohydride to it to reduce it to an alcohol, if that ketone is not in a ring, if it's just an acyclic ketone, let's take 2-butanone as an example, then when I add sodium borohydride to this, I'm going to get a simple racemic mixture of enantiomers. So here, there's nothing that dictates whether the hydrogen comes from the front face or the back face, and so I'm going to get both products. Here, if my hydrogen comes in from the back face, and here, if my hydrogen comes in from the front face, I'll get a 50-50 mixture of these two enantiomers. And that's generally the case for acyclic systems that don't have maybe large steric environments around them. The situation with a ketone in a ring or a cyclic ketone can be quite different. Let's just take a look at cyclohexanone, for example, and then we'll look at the actual reaction from this lab, which is a substituted cyclohexanone. So here, if I've got cyclohexanone just drawn in its two-dimensional format, again, it may not look like there's anything biasing the hydrogen to come from the front face or the back face. It's helpful to remember that here, this molecule actually is in the three-dimensional chair structure, not in a two-dimensional kind of flat structure here. So a chair for this molecule would look roughly like this, and I'd have my ketone at that position. And here we can note that there would be a preference actually for the hydrogen to add from the axial position, because that would then put the OH group in the equatorial position. So if H minus from my BH4 comes in, I would end up with essentially, if it comes in from the axial position, then I would end up with OH in the equatorial position, which we know from conformational analysis is more stable. Now, however, if I do this reaction, I actually am going to end up with essentially both products and essentially just an equilibrium. Here, actually, I don't even have a chiral center, so it doesn't really matter. You can't distinguish axial versus equatorial hydride addition because here it's symmetrical the whole way around, so the alcohol is not chiral. It's an achiral molecule. That situation changes if I put a substituent on the cyclic ring, and here it can be fairly significant. So let's say that I put a tert-butyl group here in the 4 position, and if I do that, then the molecule in 3 dimensions is going to arrange itself such that that tert-butyl group is in the equatorial position, because the tert-butyl group is a large group, does not want to be in the axial position. And in this case then, there's one other thing to keep in mind. Because this large group prefers to be in the equatorial position, my molecule will not tend to do ring flips anymore. So most of the time with cyclohexane chairs, they can interconvert between 2 different ring structures just by doing a ring flip. That it tends to be shut down mostly if we have a very large group that really prefers to be in the equatorial position, because whenever you do a ring flip, anything that's in the equatorial position moves to be in the axial position. And here, having the tert-butyl group in the axial position would be very unstable. So my conformation is essentially locked here with the tert-butyl group in the equatorial position. And now I actually can get a some distinguishing between 2 products, because now if I have hydride addition, then if it adds from the axial position, so let's say BH4, if the H minus essentially adds from the axial position, then I will end up with the OH group in the equatorial position, tert-butyl group still here in the equatorial position, and my hydride will be in the axial position. But this is a different molecule from the case where BH4 would add from the equatorial position. And from this side, that would give me a different product. Tert-butyl group still in the equatorial position, but now my OH group would be in the axial position. I would refer to this molecule as the trans molecule, the trans for tert-butyl cyclohexanol. And this one would be the cis for tert-butyl cyclohexanol, because both of these are on up bonds, even though they're not both equatorial or both axial, they're both on the upper side, and so they're kind of on the same side of the face of the molecule. So this is cis, this is trans here, and those are two different molecules. And I should be able to see now a preference for one form of addition over the other. Certainly adding the hydride from the axial position is going to, we would think that that might be favored because the trans product is definitely more stable. I'll put the OH in the equatorial position and the tert-butyl group is in the equatorial position versus the cis where the OH group is in the axial position. We would really prefer that to be in the equatorial position. Now, what we're going to do in lab is we're actually going to perform this reaction. We're going to take 4-tert-butyl cyclohexanone and reduce it with sodium borohydride in methanol, and then look at the product distribution and see what we get. See how much of the trans, how much of the cis. And the way that we really characterize this, the way that we tell or distinguish between the cis and the trans, really all involves the proton NMR of this hydrogen signal right here, the hydride that we added. Is going to give us two very different signals depending on whether it's cis or trans, whether it's the cis or trans molecule. The reason for that is due to the neighboring hydrogens. So here, I'm going to have, for each of these, I'm going to have two hydrogens on the adjacent carbon. So I've got these two axial, two equatorial, and here I'll have the same situation. Now, the axial and equatorial hydrogens are not chemically equivalent, and so they're not going to, they're not going to couple with this nucleus to the same degree. Now, one way that I really distinguish between these two is that I'm going to get a different splitting pattern depending on whether it's cis versus trans. And at first that might be confusing because you might think, well, in total, this hydrogen has 4 neighboring hydrogens, and that one has 4 neighboring hydrogens, so how would the splitting be different? Well, it turns out that in ring systems, the dihedral angle between hydrogens on adjacent carbons has a significant impact on their coupling constant, how strongly those nuclei affect each other. And it's most strong when the dihedral angle is either 0, so that would have them eclipsed, or when the dihedral angle is 180 degrees, which is when they would be anti to each other. As you can see in the trans case, this is going to be anti with that hydrogen, 180 degrees. This one's also going to be 180 degrees from this one. And so we'll have strong coupling with these two hydrogens. But the coupling is much less. In fact, it's close to 0 if we have a 90-degree angle between the two. Then we have essentially no coupling whatsoever, even though they're on adjacent carbons. Here, my angles are not 90 between the hydrogen here and the equatorial, but it's about 60 degrees. So it's a much smaller coupling constant. And so for this one on the right, the trans, what I'm going to get is these two hydrogens here will split that hydrogen with a large coupling constant. And so essentially I'm going to treat that as, okay, I've got 2 neighbors with a large coupling constant. That's going to be a triplet. So I'll have a triplet. And then I've got 2 other neighbors that also split that hydrogen, but with a much weaker coupling constant. So what that's going to do is it's going to split each of these signals into a triplet. And so I'm going to have, at the end of the day, I'm going to have a triplet of triplets. And I'm not going to be able to draw this very well, but essentially we're going to end up with a triplet of triplets for that hydrogen in the trans case. So I'm going to do this not very well. But we have essentially a triplet of triplets, kind of a bit of a mess of peaks. So how does that compare to the cis version? Well, here, because this hydrogen is equatorial, it now is not 180 degrees from any other hydrogen. In fact, its dihedral angle is about 60 degrees from all 4 of the hydrogens, which means that all 4 of the neighboring hydrogens couple with about the same coupling constant. And so we essentially just treat this as having 4 neighbors. So I end up simply with a a 5 splitting pattern. So 1, 2, 3, 4, 5. That's very distinct from the trans. And those two are going to have different chemical shift values as well. So I should be able to resolve them on the NMR. And then by simply integrating the signal that corresponds to the trans, the signal that corresponds to the cis, each of them correspond to just one proton. And so comparing essentially the ratio of those will give me the product ratio of the trans to cis. And I'll be able to see how selective this reaction is for one versus the other. And so I think that's a little bit of a brief introduction to this topic. We're going to go up to lab, measure out our 4-terbutyl cyclohexanone, dissolve that in methanol, and then add our reducing agent. Let that go for a while. We'll work up the product and get to a solid here. The starting material is a solid. The product is also, the crude product mixture is also a solid. And we'll take the melting point of that, since there is a difference between the melting point of the starting material and the melting point of the two alcohols. And then really we'll characterize the product distribution by proton NMR. So let's head up to lab and get started. Here we are in lab. I have a 5 ml conical vial right here where I will perform the reduction. I have this small spin vane. Might be a little bit difficult to see, but it's kind of triangular shaped, and it fits well in this conical vial so that it can spin with the kind of not flat bottom, with a sort of cone-shaped bottom. So I'll perform the reaction in that. I have my substrate, the 4-terbutyl cyclohexanone, that we will be reducing. I have methanol as my solvent, and then I have a solution of sodium borohydride in methanol that I'll be using as my reducing reagent. Now, I'm going to do this on a 150 milligram scale for the 4-terbutyl cyclohexanone, so 150 milligrams of this I will weigh out. I'll then add 300 microliters of methanol and 500 microliters of my reducing solution. And then we'll let that stir for a while and see the results. Now that we have let the reaction run for 20 minutes, we will carefully quench the reaction by the addition of 2 milliliters of 1 molar hydrochloric acid. And then we will extract the solution using methylene chloride. We will now extract the solution carefully with 3 1 milliliter portions of methylene chloride and transfer the lower, more dense methylene chloride layer into this clean Erlenmeyer. We'll let this stir for a moment and then turn off the stirring, allow the layers to separate, and then remove the bottom methylene chloride layer. We will now dry the methylene chloride extracts with a scoop of anhydrous sodium sulfate. This will absorb any water that's residual in the solution. We'll let that sit for a couple minutes just to absorb any water that remains in the solution. The organic extracts will next be transferred into a clean round bottom flask and the solvent removed using the Rotavap. So we'll get the mass for that round bottom flask so that we can then get a final mass with our product after the solvent has been removed. The dried methylene chloride extracts are now transferred into a round bottom flask using a pipette filter. The residual drying agent is rinsed with a milliliter or 2 of methylene chloride just to remove any residual product that may be clinging to it. The solution is now ready to take to the Rotavap to remove the solvent. We now have our isolated product, and we're ready to get a final mass, and then NMR and possibly IR spectroscopy analysis.